Chapter 5, the importance of parsimony in statistical modeling. Suppose we are fitting a regression model with 100 covariates and we identify 5 influential coefficients. We test the rest at alpha equals 0.05. We get 100 times 4.75 over 9.75, which is approximately 50% to be false positives. This is the false discovery rate. The multiplicity problem states that a sequence of multiple tests of hypotheses at the 5% level is bound to run into problems as it will end up with many false positives. How do we guard against false discovery? Controlling the family-wise error rate is one approach to the multiplicity problem. We can either do the Bonferroni method, which adjusts the alpha level for individual comparisons, or you can control the expected proportion of falsely rejected hypotheses. We use FDR equals the expected value of V over V plus S, which is shortened to be the expected value of V over R. We want to keep this value below a certain specified threshold alpha. How to test? M tests of hypotheses with M specified random test statistics, where MO is the number of true null hypotheses, and M minus MO is the number of true alternative hypotheses. V is the number of false positives, T is the number of false negatives, U is the number of true negatives. We let H1, H2 through HM be the M null hypotheses. We let P1, P2 through PM be corresponding probability values. For a given FDR equals alpha, we find the largest K such that the P of K is less than or equal to K over M times alpha. This becomes the rejection cutoff. Example 5.1. If we generate 100 of n from 0 to 1 columns of length 25, we add 1 to the first 5 columns to get the h of I to be mu I equals 0 for I equals 1 through 5. We conduct the test and get 10 significant at alpha equals 0.05 and 5 false positives at 50% rate. Next, we select alpha equals 10, and then alpha times the j over m equals 0.10 times j over 100. We calculate the p-value rejection cutoff to be alpha to star equals max of j times the p of j less than or equal to 0.1 times j over 100. We find this test to be 0.0015. Therefore, we have 6 tests that are significant. If we do the same example, for example 5.2, and we generate the same thing for 500 columns, 32 turn out to be significant and 27 false positives with an 84% rate. This isn't good. We use the alpha to be 0.2 this time. Therefore, alpha star equals max j times the p of j less than or equal to 0.2 times j over 500, which is approximately 0.002 at j equals 7. Therefore, there are only 7 significant now. We use the Benjamini-Hochberg-Yekatuli procedure to control the FDR under dependence assumptions. They modify the threshold to be alpha star star, which equals max j, times the p of j less than or equal to alpha times j over m times c of m. This is where c of m equals 1 if independent, or the c of m equals the summation from I equals 1 to m of 1 over I, which is approximately the ln of m plus gamma, where gamma is approximately 0.57721 if negatively correlated. Now we get to chapter 6, penalty-based variable selection in regression models with many parameters, LASSO. Many regression models include a very large number of covariates, especially when some of the covariates are categorical variables that have to be converted into indicator variables. We need to simplify models as the estimation of unneeded coefficients degrades the forecasting performance. The LASSO, or least absolute shrinkage and selection operator algorithm, finds a least squares solution such that the beta hat of LASSO equals the arc min of beta times the summation from I equals 1 through n of yi minus the summation of j equals 1 through k of beta j xij squared. This is subject to the summation where j equals 1 through k is the absolute value of beta j less than or equal to t. T has to be greater than or equal to 0, which is a turning parameter that controls the shrinkage that is being applied to the estimates, where beta hat is the standard least squares estimate. The lasso optimization problem is beta hat lasso equals the arc min of beta, which is the summation from I equals 1 through n of yi minus the summation of j equals 1 through k, beta j, xij squared, plus lambda times the summation of j equals 1 through k, the absolute value of beta j. Lambda is the Lagrange multiplier, which serves the role of a penalty coefficient. Large values of lambda penalize large coefficients, and the resulting lasso estimates will be shrunk to 0. Small values of lambda result in little shrinkage when lambda equals 0. There is no shrinkage at all. Shrinkage applies to the slope coefficients of the regression model. The least angle regression LARS algorithm computes the entire lasso path. Now, if we look at RStudio and we do lasso, where we set lasso to be LARS, x equals x, y equals y, and the trace equals true, this provides the lasso estimates of the linear regression coefficients for a range of lambdas. Now, if we do the coef of lasso, where s equals the combination of 1/4, 1/2, and 3/4, where the mode is fraction, s provides regression estimates of various degrees of shrinkage. Then we use the predict variable, which is used to predict the response with lasso estimates that have been shrunk to a certain fraction of the least squares estimates. And finally, we do CV of LARS, which is the cross-validation using 10 folds when k equals 10, and this obtains the optimal value of S. There are 3 advantages to using lasso. Lasso is almost automatic and works very well for models that contain many covariates. Algorithms are fast and efficient, and estimation and testing can be carried out at the same time. There are also 2 disadvantages. Lasso is scale dependent and only works for regression models. Now we get to the first example, which is prostate cancer. The data contains the results of biopsies of 97 men of various ages. This includes the Gleason score, the prostate-specific antigen, capsular penetration, and benign prostatic hyperplasia amount. The goal is to predict the tumor log volume using 5 covariates, the 5th being age. Now we get to the first example, which is the prostate file. We have to read in the data of prostate, and we look at the first 3 columns. The output of both the standard regression analysis and the lasso estimation are shown below, where we have M1, and we summarize it. Now the model matrix statement defines the model to be fitted, and we combine all of the 5 covariates. So we take off 1 from each, and stripping off the column of 1s, as lasso includes the intercept automatically. So we have to read in the library of LARS and lasso on all the data. The trace of lasso standardized coefficients for varying the penalty. So we have to plot the lasso that we found. The graph of the lasso estimates as a function of the shrinkage illustrates the order in which variables enter the model as 1 relaxes the constraint on the L1 norm of their estimates. So we check the coefficients with the S to be 1/4, 1/2, 3/4, and 1. Now the cross-validation using 10 folds, where x equals x and y equals the prostate. Now the output of cross-validation shows that the mean square error increases quite rapidly if we shrink the coefficients too aggressively. There's also another way to evaluate lasso's out-of-sample prediction performance. We take it using the dimensions to be 10, and we check 25, 50, 75, and 100. We set the seed, and then for I in 1 through 10, we set up the train in the lasso, and we check every MSE of the lasso using the mean, the mode, and the fit. Now we can check each mean. For the 25, we get 1.015357. For 50, we get 0.6797. For 75, 0.5537. And for 100, 0.5299. We do a box plot to summarize it. Now we go to example 2, which is the orange juice example we did previously. We have to read in the library and read in the data of OJ. We check the first two columns, and we set x with all of the covariates. And we check the dimension of x. The model that is specified here contains as explanatory variables the logarithm of price and its interaction with linear and quadratic components for feature, brand, and the demographic characteristics of a store's neighborhood. We know that LASSO is sensitive to scale, hence we normalize the covariates as they are of very different magnitudes, and we transform the covariates such that each covariate has mean 0 and standard deviation 1. The first column of x consists of 1s, the intercept, so we strip the column of 1s as intercept is included automatically. Then, we normalize the covariates as they are of very different magnitudes. Each normalized covariate has mean 0 and standard deviation 1. So for j in 1 through 209, we get the mean and over the standard deviation. Now, one could consider the standard regression model. We get the summary of it and we predict the regression. Or one could consider LASSO, where we have to get in Lars, and we do the lasso of x equals x and y equals oj, and we do the coefficients where s combines 1/4, 1/2, 3/4, and full. This creates a lasso estimates as functions of lambda, gives you the estimates for 4 shrinkage coefficients. Now we check the predictions in regression, and Lars s equals 1 are the same. There's 0 differences when we do the p of the difference. Out of sample prediction, we estimate model on 20,000 rows, where we do the lasso to be 10, 50, 90, and 100 with a dimension of 10. Now we set the seed, which fixes the seed to make random draws reproducible, and for I equals 1 through 10, we do the same thing as before. Now we can check the mean of 10, the mean of 50, the mean of 90, and the mean of 100, and we can set the box plot. This estimates are obtained for 10 random samples of size 20,000. They're always taken from 28,947 units, and for each sample, the resulting estimates are used to predict the response of the remaining 8,947 units in the holdout sample. However, it is a different story if we estimate the 210 coefficients on just 1,000 data points. We repeat the calculations, but now sample only 1,000 rows, instead of the 20,000 considered earlier for inclusion into the estimation on dataset. The predictions are now evaluated on the remaining 28. So we do 947 minus 1,000, so we get 27, and we have 947 rows. And we check the same lasso, and we find that the mean of lasso 10 to be the best.